So this is the new file, the combination of lecture one and today's lecture. Okay, we discussed, for those who attended, very good. We'll just do a quick recap for those who didn't attend, maybe have seen the video. It will be a quick recap for them as well. So we are trying to do a classification problem. We are just trying to go through each and every patient's data and finding out because of their body conditions like a bone condition, blood condition, lung, etc. And because of their age factor, whether they would be, eligible for an operation or not. Okay. So the context, business context of it is doctors spend a lot of time finding out whether the patients are, the patients that have come looking for an operation because of some problems, whether they would be eligible for it or not, basically. Excuse me. And we have to find out because, like, in terms of level of criticality of the patient, if the patient is highly critical, then obviously doctors look into those cases separately. But if the patient is not very critical, they don't want to spend a lot of time on it. So if we like design a model which will be, good enough to give us the classification of those patients which are like with level 1 and level 2 criticality, basically, then obviously it will save some time for them. And when I say some time, there's a lot of issues going on in American and European countries where like the patients are too high and the doctors basically are very scarce in numbers. So that's why they need AI to do a lot of their work so that they can focus on more important patients. So that's the thing. So here we have discussed like what we can do in terms of data. We did the EDA, we found of duplicates, we did a null value check, we did some statistical check, we did the outliers check. Obviously, we saw a normal distribution curve. We found out that this might be following any pattern. Again, another normal distribution curve, age, based on the box plot that we saw that they both contain age and a virological column contain outliers. Then we replace those outliers based on a median value. Okay. I also asked to try another method as Rupesh was discussing, and probably you might have done as well. When we replace with median, the variance basically gets impacted, and that's what it is seen in this normal distribution curve. And finally, then we prepare the data for modeling. So we do the label encoding, and then we saw the balance of the data. How much percentage is yes, how much percentage is no. We did the correlation check. We saw that our data is very not at all highly correlated, and only the two columns, age and criticality of the patient, matter a lot in terms of operation. Okay. And we saw some histogram and pair plots to find if there is any pattern in the data that we should be aware of. And then we saw some insights, the average age of the patients, and basically which region is the most highly impacted. We also saw that which critical group belongs in favor of operation in this data. So if the level of criticality is low, then basically the patients generally don't get operated. If it is low, then very few people get operated. If it is like mid-level, then mostly it is no, but in some cases it is high. So in some cases it is basically they get operated. So that portion is around like 60-40. In cases where criticality level is very high, then basically very few people do not get operated. Mostly they get operated. And yeah, that's the thing. Yeah. And finally, when we do data preparation, Then obviously we see train test split. We also saw that how we can make use of scaling. So we used min-max scaler. Uh, then we just simply checked a logistic regression model, and we did an accuracy check, and we saw that 68 is our accuracy for the test set that we are getting. Okay. We also have to take care about of one thing, that 60 if the test accuracy basically is very high or very low, and if the test train accuracy is basically creating a lot of difference between the train set and test set, then that difference basically what it makes is there is a possibility of um, I mean, if the difference of training set and test set is basically a lot, then possibly there could be a chance that we are overfitting. Okay, uh, when the train accuracy is low and test accuracy is high. If it's a vice versa, then we might be underfitting. So that's the case, but here we can see the balance. Like if it is like plus minus 10%, it's fine.
If
It's well.
if it is overfitting, we need to use that random under over sampler or SMOT technique.
If it is overfitting, then
Yeah.
first of all, you need to see whether you have. I mean, you need to just. I mean, the best simplest method would be to check how much percentage of data you have given for training set, and what's the percentage of data you have given to test set, basically. And well, like if it is overfitting, that means that the some of the data that should have gone to test set has gone to train set, and that is causing the model to basically learn a lot, but the output wise it is very low. So that's the thing. You have to play around with the train test split, and then do the iterative process of checking the accuracy after that. One thing. The other thing is, if at all, if you have any uh, problem with overfitting, you can always use sampling methods like k-fold stratified sampling, or simply k-fold sampling, and do those cross validation checks and see if you can jumble up the data in such a manner that you can avoid that overfitting as well. So there too.
Yeah, it is part of a hyperparameter tuning, adding extra weights and bias to a uh, adding extra parameter to a model.
Yes, it is. Yeah.
So, like we have a techniques are there overfitting like regularization, or else we can use SMOT or random oversampling. No, instead of adding the hyperparameter, we can try with these techniques. After
Uh,
that, we can retrain our model.
See, why I would suggest to avoid random oversampling methods, or any sampling method which is like manipulating with the data, is basically when you have like tools of like manipulating the data on in terms of weights and other hyperparameters, you don't need to do the oversampling or undersampling of anything. Okay, the standard train test split that we usually do is between 20 to 30%. Okay, if at all it is if at all you're finding that even that is creating oversampling or overfitting or underfitting, that means your data is basically very low. In that case you go for oversampling, but that is rarely a case. I mean, I haven't faced that sort of case a lot. I mean, just once I have faced, probably. That too because of not because of the uh, you know the volume of the data, but repetition of data and repetition of similar data. And that too I found out in case of image classification, so CNN. So that's a deep learning method. In that case I found out, but in general cases you'll have enough data to play around with hyperparameters rather than do the oversampling or undersampling of your training set or test set. So that's the thing. Okay, so that's why we will discuss things that we can do in hyperparameters in within the machine learning models. there's not a lot we can do in logistic regression, but yeah, a few of the things that we can do, we will discuss. So yeah, does this answer your question? Yes, sorry.
Yes, I got your question. Yeah.
Okay, good.
Rahul, one question.
Yeah.
This is the one point, like if our test data is mixed in the training data, so this is kind of cheating, that will cause the overfitting. So is there any other examples or conditions, scenarios where overfitting generates?
Uh, See, overfitting generally, I mean, the only concept of overfitting is basically when you train data, either you are sharing your train data a lot with your test data or vice versa. Okay, then the concept of overfitting or underfitting comes in. Okay, there are multiple methods to avoid it, but the concept of overfitting is like that only. The other thing is, like, if you get repeated data. So right now in numerical data, basically when you have numerical data, we have removed those duplicates. Like, we found out that 2 or 3 rows which were duplicates earlier. Okay, so we have removed it. But this problem arises when you do image classification. So if you have gone through some of the concepts of deep learning, we do image classification with sequential or
Data
non-sequential.
argumentation. After that, we can use overfitting techniques.
Data augmentation, even if you do data augmentation, what happens is it tries to nullify those features, basically. But imagine you have got like images of flowers, and they're very similar flowers, but they are taken, the pictures are taken under different lights, blue light, white light, crimson light, and things like that. Okay, and maybe taken in a lab with different sort of lights. Okay, and this happened with me when I was doing one of the projects for one of the uh, uh, banknote manufacturing companies. So imagine that you have given a banknote which is exactly the same. It's just that it has been taken under different lights. It has been crushed and manipulated in terms of, like, the note has been uh, crushed, and it is basically very what you can say, wear and tears have been created altogether, but it's the same note.
Rahul,
Take
we can use OCR technique, no, at that time, without
OC
using OCR, optical character recognition
optical
technique.
character recognition. So that's what I'm saying. Even optical character recognition technique, basically what it will do is it will try to find out the features in the notes. But what if the exact note is containing mostly 70 to 80% features exactly the same? So in that case, if you have just one particular bank note, okay, and it is passed under different lights, if it is passed under different conditions, but most of the features like banknote numbers, and if it is $100 bill, then obviously $100 will always be printed on it, and the serial number of the banknote is always there. The image of maybe whatever the image that is printed, like in our case, it is the photo of Gandhiji, and in those cases, like, it is different, but it's the same image. Okay, maybe a wear and tear is able to identify a particular level of fitness of that banknote, but obviously and that's what the problem was. Like, we had to like identify the level of fitness of the banknote. But basically what happens is the 70 to 80% features remain the same, but you won't be able to identify those features because, like, it's all it basically in neural networks, it is everything is black box, and you won't be able to find out the best features, although there is a way to do it now. But yeah, obviously that will not give you a clear picture. Okay, so what happens in that case, even though you have like 2500 images or even 5000 images, it doesn't matter. It is passed under different lights and circumstances, and it's passed for the one single node. And in those cases it becomes a case of overfitting, because whatever ratio you pass in terms of train test split, it will always overfit. So in those cases, obviously random sampling or like data augmentation and then taking out the images in different sizes, different focusing on different features altogether, and then creating images on your own, and doing that oversampling helps. But again, that case, that kind of scenario uh, was basically a rare scenario for me as well, and that will not come because obviously if you won't have different types of data, then obviously your model will not be able to learn much. So yeah, in terms of so every time, since we remove duplicates in numerical data cases, we have to take care if we are doing like processing of image or processing of sound. In those cases also, we have to see that whether the features are different or not. If they are very similar, then you will have to create features. You have to create different images which is targeting those features, and then do the oversampling or undersampling in those cases, so that can avoid uh, this overfitting. But again,
Now,
that's
like removing
in terms
duplicate
of
is also
algorithm.
a one case of avoiding overfitting, right? Because like
Sorry.
removing duplicates also is one kind of avoiding overfitting, correct?
Yeah,
Because like
yeah,
we are avoiding passing the same data and asking the model to
exactly.
correct.
Yeah. So we need to remove the duplicates in order to avoid overfitting. Otherwise, like it will overfit, obviously. So that's exactly what's happening when I discussed like the image cases. So in those cases, like you see that there are different images. You have got 5,000 different images passed under different lights and different circumstances, and they are like properly labeled as well in terms of level of fitness. Like maybe there are 5 levels of fitness, and then also you will see that it is going through a case of overfitting because yeah, uh, your training set has learned a lot, so it will give you an accuracy of 99% and things like that. But when you pass new information, new images, the accuracy will come down to 60%, 70%. So yeah, that's the problem.
Yeah,
Okay.
got it. Yeah. Basically, to avoid the overfitting condition, we generally add some variety in the model,
Exactly.
in the
So
data or randomness.
yeah, exactly. So the volume of the data matters a lot, but again, the variety, the distinction of the features matters the most as well. So these two factors play a vital role.
Okay.
Okay. Yeah. Coming back to what we were discussing. So we did everything, correlation check. Yeah. So we built a model with 68% accuracy, not bad. But in case of medical, like you might have studied this in past as well, when you might have been going through any machine learning classes earlier, might have discussed that we have different KPIs. So and always like we cannot just rely on accuracy. So that's one thing to keep in mind, that every time there would be one feature, one KPI, sorry, which will come from your business. Okay, that we want to check this. Maybe it could be accuracy, it could be in case of sales prediction, it could be uh, uh, how they would be comparing it with some other prediction, and then they will be checking and how close we are. So it could be proximity or like something like that. Okay, that could come from business. And most of the times, whatever you have studied as a statistical technique, you would be able to explain to your client or stakeholder that okay, accuracy is good or bad, whatever, but we cannot solely rely on accuracy. It can misguide us in some cases, and especially in case of medical history check and whether the patients are eligible for an operation or not. There are other KPIs that we have studied that comes from our confusion matrix. Okay, to see whether a
Like
particular.
KPI is like key performance index. Are you talking about Rahul?
I'm talking about key performance indicators. Yeah,
Okay.
yeah. So those KPIs are important to
Like
judge.
precision recall, difference score, like
Yes, exactly. Okay. So moving on to that. So Since it is like a basic model without any hyperparameters involved in it, so it is giving us 68%. Well and good. We'll see other things if we can. Like first change that we'll make is like train test split, as we discussed last time. It gives a split of 25% and 75% of the data. Now we will feed 30% of the data to the test size and 70% of the data to your train set. So simply by within the same code, same lines of code, we'll just add test size, test underscore size is equal to 0.30, and then obviously a random state as it is, and then we do again the scaling, and then we will run the model and we'll check the accuracy. Okay, so it has increased by 1%, maybe because of the size of the train and test, but yeah, it has increased by 1%. Okay, so that's one way to increase your model's accuracy. Now, to discuss other things like so last time we didn't see that how we can get the prediction. So it's a very simple method. You take the model, the object in which you have stored the model, the object in which you have like fed the data to the model, and then do the prediction. So when you do the log_predict and as the test set, then obviously you will get the prediction, and you can just find out a way like put it in a data frame and compare it with the actuals and predict it. So as you can see, actual 1 1, actual 1, and then predicted is 0. Mostly it's 1, but then in few cases it has not predicted correctly. So that means like overall 70% our model still is working fine, almost. Now we will see concept of confusion matrix. What exactly is confusion matrix? What is accuracy? What is precision and recall? What is F1 score? What is ROC and AUC? Okay, these things we will discuss. But the theory is here, and in the interest of time, if you are confident in these things, or you have like have studied thoroughly about these things, then obviously we'll not go to it. If you want, I can just go to it very quickly. So let me know if you want to discuss these concepts before moving on, because it's a part of your classification models
like
techniques
confusion
KPIs.
matrix
So you
that
might have
can
studied
you
in.
explain that tabular one, like a true positive, false positive, and false negative? Like in that, I have faced one interview question related to that. So it is alpha error and beta error. So
Alpha
in
error.
null, it is part of null hypothesis where we can see, like for example, they will give the scenario like if code people is affected, how that scenario based question related to confusion matrix.
Uh, I haven't discussed alpha error and beta error in confusion matrix in this scenario as of now. But if you want, we can like take it up separately. If you
It will
want.
be true positive, true negative, false positive, false negative. Like they will ask the scenario based question on that, like with a uh, for example, like I faced this question
But
in
isn't
during
alpha error and beta error is not
That is
solely
not
related?
alpha and beta. That is type 1 and type 2 error.
yeah, that is also known as type 1 and type 2, also known as alpha error and beta error also we can call it in statistical term.
Okay. So first of all, the thing is like you cannot simply say alpha error and beta error in false positive or false negative cases. So you need to perform probably a t-test. Okay, take a random sample and see if at all your confusion matrix that it is saying is making sense or not, whether they are statistically significant or not. Okay, so the best way to answer this question is we cannot judge the prediction right, basically right on what it is saying. If we want to perform a statistical test whether they are statistically significant or not, then we take the values from the false positive cases, and we take the values from false negative cases. And then like if it's a type 1 error, then we reject the null hypothesis that is actually true. If it is a type 2 error, then vice versa. Okay, so always answer these type of question in statistical terms, that we performed a t-test on top of it. Generally, we don't, honestly, but because we try to do try to do these statistical check on the entire prediction that we will do today. Don't worry, but we don't do a statistical test on top of false positive and false negative cases separately. If at all it is a requirement in the business, then only we do that sort of thing. But it's always, you can understand that you are taking a sample of a type of prediction that you have made, either false positive or false negative, right? And then you're comparing the data, and then you're performing the t-test, okay, to make it to see if it is statistically significant or not. That's the one case that you're talking about. The other thing that what I am talking about is I'm taking the prediction right from this area, this data frame, okay, and it contains all the false positive and false negative cases, and gives me higher chance to understand whether whatever we have done, like in comparison to two different predictions. Suppose I'm right now predicting with logistic regression, and after that I'll be predicting with logistic regression by performing some hyperparameter tuning. Okay, so the two results that I'm comparing, okay, that will give me higher level of confidence to understand whether my two models that have predicted are statistically significant or not. Okay, and that will give me the data of false positive cases, false negative cases, true positive, true negative, everything will be covered. Okay, but if you have a business requirement that will statistically, that they want to specifically focus on one particular case, then obviously you have to design two different models and then compare the data of false positive or false negative cases, whatever, and then do the t-test. We'll discuss t-test as well. If you want to perform that on top of your confusion matrix data, you can do that, separate it out, take it out, and then do that. Okay. So moving on to the classification report. So you need to obviously, if you don't have scikit-learn.metrics, then you need to install it and then import classification report, confusion matrix, and confusion matrix precision recall, and AUC, ROC, everything. Right now we have seen that we were getting 68 or 69% accuracy. Okay, 69%. But when we see that what is the precision of logistic regression classifier on the test set, it is saying 0.72, and recall is 0.68. Okay. Now, when we say that precision and recall are the two cases in which we will like compare the model, okay, which is performing better and how it is performing and things like that, you can see that basically what is happening here is when you just focus on these two, then obviously the models will give you a different picture. Okay, so when we will see precision and we will see recall, what it says is there are certain conditions. So if you go by the definition, precision is the fraction of correctly classified label cases out of all cases classified with that label value. That means, in other words, precision is a number of correctly classified cases for the label value divided by all the cases in the column. So it is sensitive to those cases, which is basically saying that whatever positive that you have, positive cases that you have predicted are actually correct or not. Okay, actually positive or not. And recall says that basically whatever true label value that you have predicted, okay, is it actually positive or not? And it is a fraction of label value correctly classified out of all the cases that actually have that label value. So right now we see that, I mean, when you go through this entire classification report, by definition, you can see that it is trying to classify two different cases, 0 and 1. Okay, and in this data, we see that it is predicting the ones in terms of recall, less in terms of precision. It is discussing, it is showing a better result. So 0.70 in terms of all the false cases and 0.68 in all the true cases. Okay, but what do you think in terms of medical terms, which case will be more important to discuss, like think it in the business context, and then relate it with the statistical terms. I just want you to give 1 minute and think over it, like which KPI in this case, precision or recall, or F1 score, whatever, will be the best answer to this question. Simply, which is the best KPI for this case that you can take up to your client and say that, yeah, obviously, my accuracy is this, but my precision or recall or F1 score is this, and we can go ahead and do this and make sure that we get better in one KPI and compare our different models. Anyone?
Session.
Precision. Why?
Like here we are mainly focusing on like medical things. So the actual positive, how many we have correctly predicted as positive. Suppose if one is having cancer, are we correctly predicting like he's suffering cancer or not?
But what you have said is correct, but what the concept wise, it should be recall. Okay. Why?
Because the
Because
actual positive, we are looking about the actual positive values. The proportion of
exactly.
actual positive is correctly classified.
Yes.
So the
So
person,
actual positive should be correctly classified. Yeah. Yeah, Rupesh. Yeah, please. Sorry. Go ahead if you want to discuss more.
basically the person which is actually having a disease, and model is also saying that is, and is also correctly classified, then that should be the case.
Yes, exactly. So in this case, in our case, basically, what happens here is basically what our data says that if a patient is eligible for operation based on their body condition, okay, if that person is eligible for operation, then they should not be denied operation because their body says it, our model says it, then well and good. Okay, they should get operated. If at all we have predicted in cases where they should be true positive, but we have labeled it as negative. Say suppose they are eligible for operation, but they are denied an operation by our model, then doctors can still look into it, okay, and decide on their own. But imagine if a person has come to the hospital and they want to get operated, and based on our AI prediction, doctors send them home and next day they die. Okay, then that becomes a problem. Okay, and if at all our model says that due to some statistical significance, some statistical numbers, this patient is not at all eligible for an operation, then obviously we I mean, doctors can reevaluate the condition based on the level of the criticality of the patient. Okay, and then take the case further separately, manually, and then decide whether the patient should be operated or not. Okay, so you might have heard about uh, cases in which uh, doctors deny a bone fracture operation to patients above the age of 80 or something like that, because their bones basically do not they do not fix at a very rapid rate, or there can be due to medication and due to the pain level, there can be cases of heart attack as well. So these are the things that are taken care in medical cases, like whether they would be able to perform the operation correctly or not. So right now the medical uh, uh, obviously medical has advanced a lot, but a few years back this was a general scenario, like 20-25 years back. Okay, patients were denied operation due to these factors, and like if the patient's condition is deteriorating, then obviously they can come back and get themselves checked. But if at all they are denied on the spot, then that becomes a problem for them. Okay. So in this case, and in most of the medical cases, just remember this, recall is always a very go-to KPI. Okay. And we will try to see if our model is improving the recall or not. If you want to get a feel of confusion matrix, it's exactly the same. just giving you the numbers. Okay. And in our cases, like in our case, basically it is predicting true positive 250 and true negative 269, and this is statistically showing the better number in terms of the prediction that we have made, because cases of false negative and cases of false negative and false positive are fairly low. Okay, but still it is not good enough for now. So we can obviously try to either do some data manipulation, maybe if you have, or you can simply try another machine learning algorithm. Okay, but before that, we can check AUC and ROC curve. It is very much resonating with our accuracy. So it is resonating with accuracy. It's saying 69.26 as a percentage of AUC. Area under the curve just significantly means that it's a strong indication that our model has been almost 70% being able to give the correct prediction. Okay, and in 30% of the cases almost it has not predicted very correctly. That being said, we can always improve. Okay, but again, it is a representation of how accurate our predictions were. But in terms of medical cases, like we cannot simply rely on AUC and ROC curve or accuracy. We have to see the KPI, which is recall. Okay. Now,
Rahul,
we
one
will,
question. Sorry to interrupt.
yeah, sure.
Can you go above in the confusion matrix part? Above one. This one, yeah. Classification report. Actually, we are predicting here for 0 and 1 classes, correct? So
Yes.
here the values are like in the recall case, if we see is 0.70 and 0.68, and in F1 score 687. What does it actually mean? Can you help to interpret those things?
Yeah, of course. So, uh, so it says that in case of recall, 0.68 says that in cases where operation should have happened, like one, the eligibility criteria of the patient, if the patient is allowed to get operated, that means it's true and zero is false. And in 68% of the cases, our logistic regression model, okay, says that the patient should be operated. Okay. In cases of the negative ones, like where patient are denied operation, 70% of the cases, recall says that patient should be denied operation. Okay. We will, in this recall also, we will focus mostly on this part where the operation was, the patient was eligible for operation or not. Okay. Even because even if the zero values are low, okay, in case of a recall, okay, then also it's well and good, it's fine, and you can see it is resonating with the one. So if you just check the overall recall score, okay, you can see that recall of logistic regression classifier on test set is 0.68. It will say the same thing over here. It will not say, even though the number is high in case of zero, it will not say 0.70. Okay, it will always say 0.68 because they are focused on true positive cases, right? And we are also, in terms of business, we are also focused on true positive cases. So this means that it has been truly able to identify those cases which are actually true positives. Okay. And right now, what it says is like 68% of the times, if a patient was eligible for patient, our model says that they were eligible for patient operation. Okay. And in terms of F1 score, it's an amalgamation of a precision recall. So it is basically a harmonic mean of precision recall. Okay. In most of the cases where you're not sure whether you can choose precision or recall, you can always take a harmonic mean, which is basically an F1 score, and say that we're not sure business wise which one would be the best option. So you can go for F1 score. Okay. So that's a way out in terms of statistics. But yeah, obviously, if you are very sure, and just like we are very sure in this case that we need to take care of recall, then obviously we do the recall. Okay.
And also we need to basically increase that value of recall, correct? Because in case of
Yes.
medical, these recall value should be close to 1.
Uh, Not always one. I mean, if it's one, then
High,
yeah,
high
they
as
get
possible. High as
yeah, highest
possible.
possible. In my life, I haven't seen going past 90%, but yeah, obviously, uh, but I'm talking about industry-based data, not obviously Kaggle data.
Because in the medical care, if this data is you can say we are relying on this data, then 30% of the chances we are not able to decide whether the operation will be happen or not, correct?
Yes, obviously. But yeah, I mean, they also understand that our model, and even doctors make mistakes. So they also understand that uh, if a machine learning model thinks exactly the same way with the same type of data, okay, finding the pattern in the data, obviously there can be exceptions, and they're not they won't ask you for 100%. They can ask for as accurate as possible. Considering that it was performed on the entire data data set with 2 million patients, more than 2 million patients basically. uh, so uh, here our aim is to go as high as possible, but yeah, obviously if you reach to a level of 90%, then obviously it is considered to be a very good model. Okay.
If we reach to 90%, then 10% of the data will be checked by doctor itself.
Yes, exactly. So that means that if the doctor on an average in a month, if they are like uh, checking the entire patient's data and spending like 500 hours, then basically you're saving like 450 hours for them based with this model. And that means like, yeah, it is a very good indicator that you're saving a lot of money for the hospitals.
Got it.
But Rahul, again, they have separate the data, right? Which our model is not able to predict correctly.
Yeah. So basically, uh, so that's why the level of criticality is mentioned in the data, right? So in cases where the level of criticality of the patient is level 1 or level 2, okay, they choose to go with the machine learning algorithm. In cases of criticality level 3, where patients are denied if the patient are accepted by the model that they should be operated, they can straight away take them to for operation. But I'm talking about 90% accuracy or 80% accuracy in terms of the entire data, okay, entire true positive cases, okay. If at all they have to check, they will double check for the level 3 cases, the high critical patients only, and that value becomes narrower when compared to the entire data, okay. So that also saves their time, okay, because if the patient is not very critical, they can simply ignore to or simply not choose to operate at that moment as well. So that also happens. So depending on the priority, they take the decision. But this also always helps them because they do not they right now they don't have to spend a lot of time evaluating the criticality and evaluating the criticality of the patient and evaluating those patients which are not critical. So yeah, obviously then they will take this prediction, filter out the level of criticality of the patient, then they will filter out whether they are eligible for operation or not, and then that becomes like 7-8% of the data which they can obviously evaluate and check if the patient should be or should not be denied operation. Okay. Does this answer your question? Sorry. Or if you
Yes,
have
Rahul.
confusion.
Yeah. I got it.
Cool. Okay, so moving on. So yeah, this is AUCI. Before going to logistic regression with hyperparameter tuning, what we can do is we can discuss those cases in which we didn't in which we uh, basically replace those outliers with median value. In this case, you can see this is a different notebook. Sorry, this is a different notebook, and what happens here is basically we are just removing those outliers. Okay, and last time we discussed how to check outliers. In this case, we discussed that replacing the outlier through a median value, we simply manually entered some values based on this normal distribution curve. Okay. And then post that, we decided whether we should replace those values in with the help of median or not. Okay. But now, today we will see some other method. Okay. Uh, and I wanted you to try it, but that's fine. If at all there is a confusion with the last method, we will clarify that as well today. So yeah, moving on. So this is the patient data which we saw. We remove the duplicate rows. We remove the null values as well. Okay, yeah, same thing. And then we didn't go to analyze the data altogether. We just focusing on data which is not having outliers. Okay. So I've clearly commented this function because some of you might be having issues with how basically we have designed it. Okay, or how basically I've designed it. So I'm defining a function to find outliers. Okay, I am feeding this function with patient's data, the entire data, and I'm focusing on two columns. Okay, age and urological, and then I'm setting up a threshold value. Okay, we'll discuss what is threshold. Based on Z scores, okay, we can obviously take out some of the outliers. Okay, so you know Z scores, what happens when you see Z score. If you're not, then obviously you need to go back to your statistics classes, and then you can move ahead. Okay, so Z scores. Okay, so patient data, age, and urological are two columns that we will focus on. Okay, and we'll take the mean and we divide it with the standard deviation, then it gives me a Z score. Okay, by the definition, by the formula. Then we will separate out those outliers. Okay, find the rows where the absolute Z score is greater than threshold. Okay, and we'll set the threshold later. Okay, so right now what I'm doing is I'm just taking the Z score from here. Okay, feeding it to the outliers object. Okay, in it, and taking the absolute value, and if that absolute value is greater than the threshold value, obviously for age and as well as for urological, so I'm taking it both, like age and urological both, and excuse me, if it is greater than the threshold value, well and good, it is an outlier. If it is not, then obviously it's a non-outlier. Okay, so I'm filtering outliers and non-outliers all together inside the function, and then I'm returning that those two objects, outliers and non-outliers. Okay. Then finally, I'm setting up a threshold. You can adjust the threshold. Either you want maybe 2.5 or 3, whatever. Just set up a threshold. I've set it to 3, standard value of Z. If you want, you can change it. Obviously, it won't matter. It will just change the numbers of outliers that you've got. Don't increase it more than 3, because the standard is like 3. You can reduce it as per your case, as per your usage, but you should not increase the threshold value more than 3, because that will give you a wrong number, wrong indication. Okay. Now what I'm doing is I'm taking non-outliers and outliers both, and taking the function find outliers and just returning all the values. So patient's data will come up, the entire data frame in which we are getting all the data. Then age and urological we are passing, and obviously we have defined threshold value, so that is also passed in the entire function. Okay, and then we're just printing non-outliers and outliers all together. So these are the non-outliers, these are the outliers. If you want to see it in a data frame, basically I've just copied it as patients underscore O means outliers, and patients underscore non-O as non-outliers. So you can see there are 106 rows in the combination of age and in the combination of urological column, which is saying that these 106 rows, although in terms of bone, blood, skin, lung, etc., they are not outlier. They cannot be considered as outlier. But you can see in a urological condition, 1463, 9197, 10,000, and in values like 498 below some 400 value also, it is considered as an outlier. Okay, due to this urological column, some of the age like 21 and 75, 73 is also considered as outlier, but we have to take the entire data frame out of the equation when we are discussing these. Okay,
Sorry to interpret. Like, what is that threshold equals to 3?
Okay, that threshold is basically a value set for Z score. Okay, so
Okay, is that mu plus 3 sigma, right? That threshold equals to 3, like mu plus 3
yes,
sigma.
yes, and when you calculate that particular thing, then the Z score, basically the default value of Z score turns out to be 3. So anything which is greater than 3, I mean Z score
Yeah,
value
got it.
considered as outlier. Okay.
Yeah, thank you.
Rahul, their Z score is a data frame, right? The
Z
first
score.
part, calculate Z score for the specified column. The first part in the function.
Okay, this one. No, it's not a data frame. It's just calculating value for each and every time you are passing information inside a loop. It's not a data frame. Okay.
But we are using it with the help of Z in the second command, outlier is equal to patient, Z score, and age. Not here, after that line.
Okay. Here.
Yes, yes. Z score of this age.
Okay. Okay, I haven't defined it as a data frame, but yeah, obviously it is taking 2 columns from a data frame, so it has converted itself to a data frame. Yes, it is a data frame, right? Yes, thank you, Rupesh.
And Rahul, here are we using Z-score to detect outliers and remove them in the for each column, or are we using for aerological also?
Both.
So, but urological is not normally distributed, right?
No, it's not.
Then we should not use Z-score. Is that correct?
No, it's not the case. Like, you can use Z scores even if the data is not normally distributed. If it is normally distributed, it won't have outliers anyway. So if it is normally distributed, if the data is normally distributed, okay, that means that basically it's not rightly, I mean, the data is not skewed. Okay. But in our case, it is skewed because it is having outliers at both ends, right? It is. So when we saw the last class, yeah, we saw mean and median value, right? If at all mean and median overlap, then obviously we can consider this data as normally distributed. If it doesn't, then it's not normally distributed, right? So it's not normally distributed, but we can find outliers in those cases, and you can cross verify as well, right? From here, we set up a value of maybe 1380, as I remember. Okay, yeah, 1380. And whatever value which is less than 1380 can be considered as a correct value, and whatever it's not, then we are replacing it with the median value. Okay, so and in case of age greater than 60 and less than 85. Okay, so you can verify it without the outliers. You can see that all the values which are greater than 1380, so even 1463 is coming up as an outlier. Okay, and these values 498, 797, 626, it is because of this particular age -10 to 20, 31. These are considered as outliers. Okay, so that's why these are also coming into picture. So it's kind of a trade-off that we are playing, because more information that we didn't want to remove from age column, okay, we have removed because of urological. Information we didn't want to remove from urological, we have removed it because of the age column. Okay, but we want to see how it can impact, how statistically how it will be impacting our overall prediction. And so the best way is to separate out that data and then do the prediction. Okay, obviously I have not performed any sort of prediction on the outlier data, but that's your job to do. You just simply have this data, patients underscore o. Okay, and you can perform some statistical checks and perform a machine learning algorithm on top of this data. Okay, what I'll be doing is and you can use the same code. You just have to replace that data frame's name on top of patient underscore no. Okay, so no outliers. In this case, there are 106 rows which has been removed from the entire data set. So 2500 rows you can see that we had. Now if you remove it 106, then 2394 is what we have left with. You can see the patient's correlation. It is not heavily impacted. You cannot see any value which is like 70 or 80% correlated, just in case of if you want the age and criticality of the patient. Sorry, operation.
Even the values are less and also in minus.
37. So it has, so when you remove, it is not impacted, like it has not impacted in terms of very statistical significant value, like 80%, 70%. So we were having 28%, I think it was 28 and 38, probably. Yeah, 28 and 38. Now we're getting 27 and 37.90. So it's considered almost 38 and 27.47. So maybe 0.5 a hit it has taken in age, because, and considerably so, because like there are more outliers in critical in urological, but because of that our age column has been impacted. So that's why the correlation has also impacted in terms of age and in terms of criticality. But rest of them are like has not improved at all. Like it's still the 2 or 1%, which does not contribute much. Okay. But that being said, our urological column with when we compare it with operation is also saying that our I mean the correlation is 1% basically here. So my question to you guys is whether it will have a huge impact on our prediction or not. Is it like worth spending a lot of time on it or not?
Can you repeat the question?
Yeah, sorry,
Yeah, sure. So right now, what you can see after removing outliers, so you can see I've taken the correlation of patient underscore, not no outliers dot core. Okay. The urological, when compared with the operation column, okay, it is giving me 1%. The correlation coefficient is 0.01. Okay. So my question to you is, even if we remove these 106 rows because of, and mostly because of this urological column, will it impact heavily on in terms of how accurate prediction we are trying to make?
Actually, earlier it was also not too much highly correlated. So this time also not too much highly correlated. So
Exactly.
I think we can go with it.
Yeah, but it's always good to check if it is like making a significant change or not. So in terms of urological, it was like negative 0.02. Now it has at least gone to positive, so it has improved like 3%. But again, it is not giving us that significant change which we were expecting. Like because sometimes outliers basically throw numbers, go to that extremities where you cannot create any sort of pattern at all. Okay, now sometimes when you remove those outliers from the main data set, you can see that the data has now found out a pattern, and gives starts giving you a better coefficient correlation. But in our case it has not. Okay, so that's why removing them will not impact the accuracy of the data much. Okay, and simply even though and coming back to the first question that you asked in terms of variance of the data as well, Yogesh. Okay. Even though the variance gets impacted when we replace those outliers with median, okay, in this case, it is not an important feature for my as a deciding factor for the operation. So even though the variance of the data in this case has impacted, if we replace those outliers with median value, okay, it is not making any significant changes or in the accurate prediction of our model. Okay, so even if you replace that particular those particular outliers with median, it's fine. If you don't, then also it's fine, you can remove it. In both cases it's fine. If you see a statistically uh, significant change, okay, huge change in coefficient of correlation or variable importance if you calculate it, okay, then only you go for separating out the data, and then only you go for separate analysis. Okay, otherwise it's completely a big waste of time to do those checks, because even if you find a pattern in this urological column, okay, and do a separate analysis and feed it to a different model, then also it won't give you any fruitful result per se, because it will again consider the factor of age, and level of criticality as its most important feature rather than considering urological. So rather than spending time to separate out the data and rather than designing a model separately for it, it's the best to check whether it is highly correlated with your y or predictor variable or not. If it is not, then don't spend much time on it. Okay, stop your operation at this point and then feed your model with the entire data that you have prepared previously. Okay.
So basically, you mean to say that if the correlation is changing much effectively after replacing with median, that means we are manipulating the data, like we are changing the original form of the data.
Yes.
So in that case, we should go with different analysis, like we have to separate the outliers and then perform analysis on that data, right?
So there are both cases. If you have replaced it with median, and if it is like giving you a statistically significant change in terms of correlation, well and good. Okay, it should be as normally distributed as possible. Okay, you can do a model building on top of that, or you can separate it out and check if you have removed those outliers, has it made a significant change or not in terms of correlation. If it has, then obviously you should remove those rows from the main data set and perform the analysis, perform the model building on top of the data set which is free from outliers. Okay, if it is not, then if it is not making a lot of changes, then stick back to the previous method by replacing it with median and then simply go ahead. If it would have been say suppose made a significant change in age, so right now it is impacting like 0.5%. Okay, 0.2% in terms of criticality. If it would have been like made a huge change, like went up to 60-70%, then it makes sense to give more importance to that particular data and do a separate analysis. If it is like impacting like 3%, then obviously it won't bother much to your overall prediction, because mathematically, if you will see, say suppose age, bone, these are the 12 columns which we have in the data set. Out of that, 9 are considered to be the best features of it. Okay, and if you divide 100% by 9, okay, it will just come out to be 11 point something. Okay, so and each data point from one particular column, okay, is contributing to 11% only in terms of weight of the data. Okay, so that 11% becomes very low when we talk about dividing it into 2500 rows. Okay, or if you take it train test split, then 70-30, then obviously maybe whatever it is, like 70% of 2500 rows, and basically, so that will come out to be 750. So 1850 divided by the 11%. So that number will also be very, very low. I'm talking in terms of weight, how weights are calculated mathematically in a machine learning model. Okay, so that becomes a problem when the coefficient of correlation is very high. But if it is like impacting very low, like 11% of 3%, okay, I'm talking about 11% here. It has made a change of -2% to +1%. Where is it? Yeah, this one, +1%. Okay, so that 3% is the statistical change from correlation coefficient from the previous to this one, and that means, and the weightage of this particular column ideally is only 11%. Okay, and that change is only 3%. So 11% of that 3% is again a very low number, and that is divided by 1850 rows. Okay, so that becomes a very, very tiny number. Okay, and that sort of impact in your entire prediction will be very, very negligible. Okay, so that's why it's not important to spend a lot of time on it, because you can see, and that's why like mathematics and how weights are calculated, these things play into picture, and you also do this analysis as a good data scientist. You have to see these things to find out whether it will heavily impact or not. Maybe it will impact if the number of rows are just 10. Maybe it will definitely impact. But if the number of rows are very high and the change that it has made after removing those outliers are very low, and the weightage that it has is only 11% comparing to the other variables that we have, then obviously 11% of 3% and 1850 divided by that value. So it becomes very low. Okay. So that's why we should not spend a lot of time on this particular column, because it is not statistically giving us very good coefficient of correlation. But yeah,
Rahul, one question. Sorry to
Yeah.
interrupt.
Sure.
Actually, if we are removing the outliers, okay, and removing the outlier for a particular column, and after that we are again checking the correlation coefficients, it may also happen that some of the coefficient for other columns are increasing too much, correct?
Yes, it can. Yeah.
So in that case, we should avoid this method, right?
Uh, no, Rupesh, because like I say, see, if at all, see if you compare the two independent variables. So suppose this is like 17% now, blood and bone. Okay.
Mhm.
If removing those outliers means that it is finding an exact pattern, okay, which is rarely a case, because it can happen in case of urological and maybe say is nothing. Yeah. So minus 23. Even if it is negative, it is following a pattern with heart. Okay. Urological. Okay. Minus 23. If at all, it is basically following a number which is going up to 80% or something like that, then you will see that the entire column should be removed. One of those columns. So suppose right now it's 23. If it is 83 with heart, so either the heart or urological should be removed after removing the outliers. Okay. So these checks also you should do, obviously. But we cannot discard the method that we need to remove the outliers altogether if we see that it is following some sort of pattern. So we moved ahead with this method because we saw that it is following some sort of pattern. Again, where is the normal distribution curve? Yeah, we saw that it is like separately following a pattern. Okay, but we also know that it is the outliers are starting from this black line. Okay, so this is also these are also outliers. There are some numbers here, and it is also following a pattern over here. Okay, so that's why, and these numbers are altogether not at all impacting on our predictor variable, so operation initially also. Okay, so even after removing that, it has obviously improved by 3%, but it has not improved that much. Okay, now the next thing is to just check if at all it has improved in terms of multicollinearity or not. Okay, so if it is a urological column, and if it is like making a change after removing those outliers in terms of in comparison to other variables, then obviously you need to remove those variables, one of the two variables. Okay, but again, before that also you'll have to check whether it is going to impact or not, whether my so ultimately we have to find out whether the operation whether the patient is eligible for operation or not. That's our main target, main goal. Okay, so even we have to check whether it is impacting on our uh, operation criteria or not. If it is not, then it doesn't matter. Okay, we go back to replacing the outliers with median and follow the procedure. Okay, if it matters, then obviously you need to remove one of the columns. Okay, and then move ahead with the further analysis.
Okay, and can if we remove the outlier from the urological column, can it impact the others columns like lung or skins? Their values can be high.
It will not be yeah, it I mean, since we are removing all the values here, so you can see 106 rows
Ah,
are
okay,
all removed, so it will definitely impact. Okay,
okay, okay.
it will improve or decrease it, but it can or cannot. Okay, obviously you need to check.
Okay, that point is good. If it is increasing the other independent variable coefficient correlation, in that case, if it is very high, then we can remove that also.
Yeah, exactly. Yes.
Okay.
Good question. Okay, now we do the label encoding last time. As we did last time, we do the train test split, we do the scaling, and we do we call the logistic regression, and when we saw that it is giving us 65, 67, and it is giving us a recall and precision of 67. So it is basically not improving the accuracy, but it is very much saying that all the true positive and true positive cases which are actually positive and true positive cases which should be positive are both basically very much in balance. Okay, so if you remove outliers, if you remove those outrageous extreme values, obviously it improves the prediction overall, but not to a very high significant level. Okay, so those things that we have discussed just before, like few minutes ago, for the entire data set, where we replaced it with median value. Same thing you can check, you can compare the value. It is coming out to be 67 in terms of recall. Here we were getting good 68. Yeah, 68. Okay. But one more thing is like removing those rows basically impacts the overall data as well. Okay. So now the number of data has reduced from the entire data set. So when you do the train test split 70-30%, it will obviously impact your size of the data as well. Okay. So that's the problem. And sometimes uh, it becomes a very big issue in terms of like we are reducing the data and we have to check it with the client that we are reducing the data, and we do a separate analysis and blah blah blah. But again, if you see that it is if it is like giving you a more impactful change in terms of coefficient of correlation, accuracy, recall, precision, whatever, then you have a strong backup to say that we are removing these values because they are outliers and we want to treat them separately. Okay, but if it doesn't, if it is like a change of 1 or 2%, then obviously it won't matter a lot. Okay, so any doubts until this point? Perfect. Yep. So again, AUC has also dipped down because of the size of the data. And yeah, obviously, this is something which we haven't discussed. So this is basically a logistic regression with hyperparameter tuning. Logistic okay. So when we do that, it has thrown some warning. Ignore that. When you go to the very bottom, you will see. Just a minute, I'll be back. Sorry. Yeah, so we'll go at the very bottom. So best is what we are getting is 65.49 in terms of accuracy. Okay. And it is identifying the most important feature. We'll discuss about these features in the main section. Okay. This is after removing those outliers. Okay. So 65.49 in terms of accuracy. So it has reduced the accuracy. But again, when I said at the beginning, accuracy does not tell the entire picture. Okay. So you can see what is C, penalty, solver, these things we will discuss if you don't know it. If you are comfortable with it, then we will. Then we will not, obviously. Yeah, but what it means is like here in this case, we are just getting values in terms of it is just trying to do an iterative process. We might have heard previously that it obviously grid search CV does an iterative process by checking all the values that has been given to it. So in our model logistic regression, we are giving solvers, penalty, C values, and it's trying to find out the values which are like going to improve the prediction or not. Okay, and basically it tries to beat out the error and finds out the minimum, the most least error in a combination where it can find out the least error and most accurate method. So scoring criteria here is like accuracy, You can set it separate, different scoring criteria as well if you want. For now, we'll keep it to accuracy, and then obviously get the best accuracy in terms of the combination of the hyperparameters that it has chosen. Okay. There's another way to do it. Okay. So if you don't want to see what is happening in the black box technique altogether, here we can see this is a separate set of code where we can get the summarized result in terms of considering all the factors like mean test score, standard test score, and parameters all together, and then find out the best features. Okay. If you don't want that, okay, you just want to stick to the best hyperparameters and the accuracy, you can avoid that, and obviously you will get a different sort of result. Okay, just one particular value. It's up to you whether you want to get it separately or all together. That's up to you. Here in this case, I have shown two different ways to do it. Okay. The difference in this is like there are few changes in the hyperparameters. Okay. Even in your grid search approach, you can either choose to, give all the factors altogether, all the options that you want to. You can hide some of the factors, or you can increase or decrease some of the parameters in your parameter grid. So this is parameter grid, and find out the best hyperparameters and find out the best results. So in this case, I have improved it by just 1%, 65.49. Not making a lot of change, but yeah, obviously 66.27, like 80.80 kind of improvement. It's because of the penalty factor that I've included, L1 and L2, which is giving us the regularization method L1, L2 regulation. If you know, you might be understanding what I'm talking about. That helps to improve the results, and these are the best parameters. In this case, I've just kept it to L2 because it is considering all the test scores and everything. And if I give the penalty factor L1 and L2 both, then it will take a lot of computation time. Okay, so these are the factors that you have to consider before running the model as well. Logistic regression can be very simple and straightforward, as we have seen here. It's a one-liner code. Okay, and it can be as complicated as you can see here. It's not very complicated, but yeah, I mean, compared to that, it is complicated, where we are considering all the factors. We'll discuss these, but right now I'm just like focused on the result. After removing the outliers, the recall is 65. So the thing is, basically, logistic regression was able to find out will not be able to find out a pattern in the outliers mixed with the main data set. It will confuse. But if at all, it is rightly manipulated, like if we are replacing it with median and it is not making a lot of significant changes in the data, then obviously it will throw out significant improvement. Okay. Now, if I change the test size and rerun the model, this is 25. So it has gone to 66.48. And if you check the recall, prediction log. Okay. Yep, 66.48. And then you can see the recall has increased to 66. So basically it was taking the values from this particular bit. So it has improved from the accuracy also has increased, and recall also has increased by 1%. You can see the same changes, few similar changes over here. Right now the AUC is 0.64. I don't think it will make a lot of change. 6.5, just 1% increment when you change the regularization option. So here we are giving only L2 regularization, penalty factor, and here we are giving L1 and L2 both. Okay, although it is taking L2, and also the most important method, solver method, it has taken as Newton method, and here it is a linear, but obviously yeah, it is not being a lot of changes, but yeah, it has improved it to significantly a very less value, like 1%, or maybe yeah, almost 1%. Similar changes you can see in recall, similar changes you can see the AUC and ROC curve. Now what has happened here is basically we have removed these outliers and formed the analysis on top of the data which is not having an outlier, any outlier. Your job is to take the same code and run the data which is just outliers and see what is the accuracy that you're getting. Okay, so run the model, both the models, when I say model, with hyperparameter tuning and without hyperparameter tuning as well. Run the models with the patients. Oh, okay, so that will be your homework, so that you will also get a feel at what we are doing here. Okay. So yeah, logistic regression with hyperparameter tuning. Basically, what happens here is we are trying to give some hyperparameters. Okay, so what are hyperparameters? You might be knowing, just to give you a brief information about hyperparameters. So there are things that you do in terms of data to improve your prediction, and there are a few things that you do in terms of mathematically how you can improve your model. Okay. In order to improve your model mathematically, in order to improve your predictions mathematically, okay, there are a few things that you do with your model which can improve the final prediction, improve the results basically, and those mathematical operations that you perform are called hyperparameters. Okay. And this model, we are taking logistic regression. Solvers are basically you can see solvers as the sub algorithm inside the main algorithm. Okay. So there you can see Newton, CG, SAG, LBF, GS, liblinear. These are all solvers which help to improve the prediction by reducing the error. Okay. And the penalty factor is basically it beats the error as well. So it allows you to regularize some of the data points which can point to some extreme values. Okay. And those factors are regularized by penalty. And these all come into picture when we put it into a grid. Okay, and take a combination of these solvers and penalty and these C values as well. Okay, 110.1, things like that. If you want to get to know more about it, just press Shift Tab on logistic regression. You can see there's penalty, there's dual, toll, a lot of things, max iter, whatever you want to put. And when you see penalty L1, L2, elastic net, none, default L2 is there. And if you want to get more information about what is C, so it's inverse regulation strength, must be a positive. And when you want to know more about solver, so these are the solvers that we have. Default is LBFGS, but yeah, algorithms to use the optimize the problem. So as you can see, these are all algorithms, but it is optimizing the problem, basically a sub algorithm within the main algorithm. Okay. And that's why these things come into picture when you try to improve the prediction, because now they are all coming all together to beat the error, reduce the error, and give you the better prediction. You can use other hyperparameters as well, as we have seen here, solver, max iter, although we have used most of it, but you can use if I have missed something, That won't make much of a difference, but yeah, if you want to see that if we add these things, then how it can improve or degrade the quality of prediction, then you can use it. Okay. Obviously, Newton's method is used. So within the solver, there are multiple methods that we have seen. Newton's method is used for multi-class classification, but it can very good. But I mean, it's the entire information is not here. But yeah, obviously, Newton's method can or cannot be used for binomial classification as well as multi-class classification. For multi-class classification, you cannot use liblinear because that's the only check here. So liblinear for small data sets, it's a good choice, it says. Saga is faster if you're not getting very much difference in terms of improving the prediction, and if you want to do faster operation, then you can choose Saga. For multi-class problem, Newton's CG, Saga, SAG, and LBFGS are used. Liblinear is limited to one verse rest scheme. So basically, liblinear is used for binomial classification. Okay. So apart from liblinear, you can use every other algorithm as a sub-algorithm or as a solver to optimize the problem. Okay. When we say optimize the problem, it is just basically means that we are trying to reduce the amount of error in each and every step, in each and every iteration. Okay. So these things help. One of the example that liblinear you might or might not be knowing. I won't go into details of each and everything. Newton's CG is basically one of the most influential algorithm, Newton's method. It is influenced by Newton's method. It is close to something which we are trying to use in research methodologies. So Newton method is something which was derived out of Newton's research. Okay. And basically, if you have any idea about gradient descent, then you will be able to understand what I'm talking about right now. If not, don't bother. Use it as an hyperparameter, and that should be fine. You can study about it later as well. But Newton's method is basically based on a vectors concept. So talking in mathematical terms, vector is basically something which gives you a direction as well as magnitude. Okay. So when you go to again, when you go and study about, or if you know about the gradient descent method, then gradient goes to chooses a downhill approach to find out the global minima. Okay. And global minima, when it reaches to the global minima, there's something called local minima and global minima, but I won't go into details of that. Global minima is basically a downhill approach in which if you're at the top of the hill, imagine you are at the top of the hill, you take one step at a time and go to find out the minimum error. You roam around to a particular area, find out a local minima, then you choose another area, go around to that area and find out the local minima, and compare all the local minima and get to the final global minima, and choose that point as your best point of interacting with other data points, because that gives you the least amount of error. Now, that is the concept of gradient descent. What Newton method says is, Newton says that not only the step size, so in gradient descent, you are deciding the step size, how you have to move. But Newton method is so accurate that it follows the concept of vector entirely, and says that not only the step size, Newton's method is helpful in finding out the direction as well. So not only you are going to find out the best direction in which you should go, you are also able to find out the best step size as well. So step size as well as the direction. But in gradient descent, the direction is not there. Okay. So if you get the combination of direction as well as the step size, you get to the global minima more accurately, because the chances of finding missing out a particular area, missing out a particular spot where you can find out the global minima in route of finding the local minima gets eradicated, because it goes into the direction of global minima and takes one step at a time in that particular direction. Okay. The mathematics of it is very complicated, but with one simple line of code, basically, solve y is equal to Newton CG, you can get it done in terms of practicality of it. But you should know the mathematics of it as well as a data scientist. So that's why I'm explaining it at a very high level. Okay, very low level is pretty much could be only a Newton method class could be of more than 8 to 10 hours. So we won't go into that details. So yeah, similar concept is for SAG, LBFGS, and liblinear, but they don't follow the method of gradient descent. They follow the method of trying to find out values which can be when we compare it with the actual values from the trained data set, then it can be then it can reduce the error value basically. So but in Newton's method, it is basically the most accurate method as of now. And what Newton tried to calculate with pen and paper, we are not able to calculate with parallel computing as well because of the size of the data set. That's one thing. The other thing is like Newton was a genius. Anyway,
Can you
so
repeat for SAG and that one? LB.
SAG, LBF, GS, and liblinear, basically they try to minimize the error when we compare the trained data set with the predicted outcomes. Okay, and it compares from actual versus the predicted values, and tries to find out a statistically significant statistical value. Basically, when you study the alpha value and beta value, so similar concepts are here as well. And similarly, when you study the time series concept, where you compare the AIC and BIC value, similar concepts are here as well. So it compares two levels by comparing the final outcome of the prediction, final outcome of the model, and then tries to compare the actual versus predicted and finds out a score, and based on that it minimizes the error. Okay, SAG is significantly very simple, so that's why it's quicker as well. However, LBFGS also sees the what you can say, the degrees of freedom in the equation as well, in the data as well. So it finds out the non-linearity as well. So that's why it becomes a bit complicated. Liblinear is pretty straightforward. It follows it tries to give more priority to the linear data. So that's also very straightforward and simple. But LBFGS is complicated. Newton's method is highly complicated. So I won't ask you to go into much details into it, but get a high level idea of these things would be good. Okay. So spend some time into finding out these things. Okay. Penalty, already declaration at 1 and 2. C value we already discussed. And these things are pretty common, like the splits that we make in terms of k-fold. There is a repeated stratified k-fold, and there's a stratified k-fold. What is k-fold? Basically, you split the data into 10 different parts, and or maybe in this case we are splitting into 10 different parts, and if you want, you can split it into 5 as well, and then try to see a pattern in it. Basically split the data into test and train size, maybe 9 out of 10 times you do the train and 1 times test, and similarly you repeat the method. So there are 3 times we are repeating the entire split, and then finding out, basically shuffling the entire sample to give the most accurate pattern in the data, and then obviously putting it all together to find out the best accuracy score, and error score is equal to 0. So it won't be 0, but as minimum as possible. Our aim is to get to the 0. So as you can see, it is moving on to 64, error score is 0.02727. So at the very end, you will see that basically it is not changing a lot in terms of accuracy. But out of these things, out of these values, the best model will be found out based on the least accurate, most accurate and least error score, and that will give you the final result as the best. Within the grid search, it will find the final result, and the grid search will give you the best model, and that grid result will have the data X train and Y train, and that will get fitted into the model, and finally you can get the prediction in this spread_log_reg with the predicted result of X test, and then you can simply run around these and find out the best value by looking at it as well. And your best parameter, your grid search CV result will find out the best parameter for you as well. Okay, so that's why you can see here it is written best. As you can see here, best printed, and the best score that it is getting from grid result is printed over here. Okay.
Rahul, one question.
Yeah.
Using n repeat is equal to 3 and n split is equal to 10. So total 30 times calculation will be there. Correct?
10 repeats once, and then again that happens 3 times. So you cannot say that it's 30 times. You can say that there are 3 different samples that it is taking, okay, out of those 10 splits. So it's not 30 times repeating all together at once. It's just happening one by one, 3 times. That's the difference.
Okay, three set of splits containing
the 10
10
splits.
split each.
Yeah, 3 set of 10 splits basically, not
set of-
30.
You got it. 3 set of 10 splits. Okay.
So again, when we saw this without outliers, same thing. I'm just giving the option of regulation L1 and L2 and giving the same solver. It is just improving. Now it is improving by almost 2.5%, which is a good jump. Okay, so this is the example 2, and this is the first example. Okay. So you can choose any example, but in this case, since we are not following, I mean, this is basically when you print out these results, okay, and when you go to, if you want to check one by one, step by step, it takes into consideration of the mean, standard deviation, and other parameters all together, and then finds out the best value for you one by one, and it takes a lot of time. Okay, but if you want, and that's why I have avoided the regularization method L1 in it, because in both the cases we were basically, in this case we were getting L2, and in this case we are getting L1. But yeah, you can choose if you have a better computation power. Like I'm using Mac M1. It is still very fast, but still takes a lot of time. So, I mean, I would ask you to avoid going to each and every step and giving L1 regulation method parameter as well. But if you want, if you have time, you can choose to do that. Otherwise, the method, the different method is just to get the prediction on basis of best accuracy score, as we are doing here as well with the minimum error score. Okay, and give the option of penalty L1 and L2, and it will find out that a liblinear, since it's a very not a very large data set, liblinear, and here also it is giving liblinear is the best one, but here it is giving penalty L2 and C value 0.001 and giving the best score 65.58. In the other example, we are getting 0.01 as C value and penalty factor L1, and it is giving us better accuracy. Okay, now what does this mean to mean for other KPIs for us? So I have stored my result in pred underscore log reg. Okay, I've taken the recall and precision of it, and you can see a sudden jump. So 0.83 is my recall now. Okay, now when you compare it with the previous thing that we were doing without hyperparameter tuning, it was 0.68. So it gives you an indication that not only you have to play your part in data science as a data scientist, you not only have to play a part in terms of data, you also have to be very good in terms of hyperparameters that you're designing. And this is actually what happened. So this is a smaller, I understand this is a smaller data set and you can argue on that, but this actually happened when I was doing, when I was designing the model on the entire 2 million rows of the data. Okay. Initially, without hyperparameters, I usually do the same thing. And without hyperparameters, I check just to set up a benchmark. Okay. At what I was getting, I was very much getting the recall value similarly. But when I fed the entire data with hyperparameter tuning, it almost took an entire day to run. but that's okay. When I found that the accuracy that I'm getting is like almost 85%, sorry, recall that I'm getting is almost 85%. That made me very happy because like since I've made the changes, since I've added the hyperparameters, and now I'm getting the better results, which I can show it to my stakeholders. That gives you a level of satisfaction for yourself as well. And that improvement shows that you have done a better job. That being said, again, we need to check that how it is impacting the numbers. Okay, so you can see the true negative cases has been like significantly improved, 328, and true positive cases are also good, 182. False negative cases are also higher. Okay, so that gives me an indication that okay, it's a decent model. Okay, since it is giving most of the results correctly, but there are some level of inaccuracy in the model as well when I compare the confusion matrix with the other numbers. Okay, and my AUC and ROC score 67, so it is very much in line with the accuracy anyway. So yeah, it will show you the same results, but this means that we are getting the result and our model has been able to predict correct labels basically 67 out of 100 times. Okay, so this was the first algorithm. Okay, this was the first thing that came into my mind, and it should come to your mind, logistic regression, when we do classification problem. Because when you study data scientist, everybody will say, every tutor will say, follow the simplest method first. So that's why we're following the simplest method first. Okay, now this says that we are having data which is fairly linear. Okay, and if there are some non-linear data present, then our solver is able to handle those. Okay, and try to find out. But again, I have tried just one equation based algorithm. You can try others as well. Can you name some of the equation based algorithm apart from logistic regression which you can try? I mean, because in the next step we are moving to tree based algorithms, and I have checked all other equation based algorithms as well. That's why I moved on to tree based. But for you, for your own practice, can you tell me which is the one very good equation based algorithm that you can try on top of it?
KNN.
Okay. Anything else apart from KNN?
SPM.
Who said SVM? Sorry.
Share.
Okay. Sorry, I can get confused with the voices. Sorry about that. So yeah, yes. So yes, SVM. KNN is also a good method, but KNN is usually used when you have sparse data. Okay, if you have like a lot of sparse data, very much irregularity in the data, where like suddenly you have like 1000 value as like 10 data points you have, like, and first data point is 1000, second data point is 2000, and suddenly you get a drop of 2000. So suddenly the third data point is 0. Then again fourth data point is 500. Then again fifth data point is 1000. Then again sixth data point is 0. Things like that. Okay, so those kind of data points, if you have, okay, KNN would be a very suitable method. Okay, because it contains it performs very well on the sparse data because of its methodology, that it tries to find out the mean value and
Like
calculates.
first it will work on the test data. After that, once the output is generated, then it will execute the train data.
Are you talking about KNN?
Yeah.
Okay, so what happens in KNN is it does not usually go through the method you have talked about. So basically it also tries to learn. Okay, and within your train data set, okay, it tries to find out one central point, okay, for a particular set of data points, and then tries to calculate the distance between that mean value with the other data points, and then find, then again it's an iterative process. Again, it finds out the best suitable mean value, and based on that, it tries to learn about the data set and then gives the prediction. Okay. Why SVM is more suitable in this case? Because we are handling some non-linear data points. Okay. Within the data using solver, you can try SVM as well. I would suggest you can try it. It won't give you much better result, but the computation power will obviously eat up your entire day if you give all the hyperparameters. Okay. SVM is very complicated algorithm altogether. And in terms of handling the nonlinear data, it takes a lot of time. So you can try SVM with similar approach, grid search approach, and see how it turns out to be. For me, I chose to move on after trying 2 or 3 equation based algorithm. I chose to move on to tree based algorithms. Okay. So in terms of decision tree, we are using decision tree classifier. Okay. You can, since it's a classification problem, we are using classifier, obviously. You have different features in it: max features, max depth criteria, Gini index, Gini criteria or entropy, max leaf nodes, min sample split. As much, if you increase the range, it will take a lot of time to process. So you can imagine that each and every iteration, it is taking account of all the values. So if you know permutation and combination, it will be 1, 2, 3, 4, 5, 6, 6 multiplied by 2 here, 4, 6, whatever, and those many combinations it will take. Um, so basically, each and every time it will take an account of 4, 6, 8, 10, 12, 17, 18, 18 multiplied by 6 combinations. Okay. So in every iteration, if it is taking like 108 odd combination, then obviously it will take a lot of time to process, and that's why we should limit it to as low as possible. Okay. You can try to increase or decrease the range of these values, but obviously you have to consider the cost of running the model as well. Okay. When I say cost of the model, it significantly means that I am running it on a cloud platform, and every time I'm using that what you can say, the usage capacity, or one cluster basically, and whatever the nodes that we are trying to make based on the data, that much amount of money is being charged. So even if you run the model for the entire day, that means you are costing your company at least maybe 8,806, around somewhat around $8,000. Okay. So that becomes sorry, not $8,000, sorry, $800. Okay. And it won't be done in one iteration or one day or one time. So every time, basically, if you run it, it will cost a significant amount of money to your company. So that's the thing, that's the point, basically. And that's why you have to choose your method very carefully, and that's why people do it in a sample of the data first, try to find out the best combination of the entire of a sample. Okay. And then give that combination and run it on the entire data set. Okay. So that's the step of, and that's the move of a good data scientist. So they take few samples and they find out the best hyperparameters, best combination of hyperparameters, and then they run it on the entire data set. Okay. Just to save the time and money. Okay. When you'll run this, you will find out that the best accuracy score it is giving is 65.88, which is very much similar to what we got. But again, our metrics define something else, and we can see that the evaluation of metrics, when you see it is saying that again the recall is 83%, your precision is 7365, and similar values that we got in terms of the recall in logistic regression is what we are getting here. But $73.65, 63, And where you can see that's 328, 182, and 73, 67 is what we are getting. So very much similar to what we got in the previous occasion. Okay. And basically what it means is it's not prediction wise in terms of each patient's prediction, but overall it is giving a similar sort of result when we try to compare the decision tree and random forest. Logistic regression. Now,
Rahul,
since
one question. Sorry to interrupt. Can you explain the combination of trees that you were explaining, like this much tree will be there? Yeah.
okay, yeah, okay.
Yes, yes.
So this is a model decision tree in which max depth. So basically, how deep you want to go. So imagine a decision tree. Basically, at each node you have the decision maker. Each node is a decision maker, yes or no. Okay, again, yes or no, things like that. And then on each step, so that one node basically gives you two different uh, branches. That it will be helpful for predicting whether at that node it should give prediction yes or no based on a criteria. And that criteria is either Gini criteria or entropy criteria. Okay. And again, to what level you want to go. So up to 10th max depth I want to go. Okay. If you want to increase it, you can increase. If you want to decrease it, you can decrease. So each depth when I'm talking about, it will contain two branches and a node. Okay. And similarly, for each tree, for each decision tree, if you give leaves, so it will have up to 8 leaves. So basically, if you want to go to max leaf 2, 4, 6, 8, whatever, okay, based on the number of variables that you have, you can try it, you can have it. Okay. So as you can see, it is also trying to find out the best combination max leaf node 4, 6, 8. Okay. And so imagine one node, and in that different branches are coming out to give you the result, the binary result. Okay. So in this case, basically the max leaf node is 2, which is giving us the best prediction. But yeah, leaf nodes are basically the branches that I'm talking about in a tree. One node will contain one depth, okay, up to maximum level 10 depth. That means 10 decision tree, 10 small decision tree are connected all together to find out the best possible outcome based on the criteria, which is Gini or entropy. Minimum sample split that it is taking. So each time it is taking a split of samples. So each time it is taking a minimum samples from the data is like 1, 2, 3, 4, 5, up to 5 samples it is taking. So as you can see, the best parameter that we have got when sample split is 2. Okay, so 2 sample splits, it has decided that this is the best factor. So it has taken one sample from the data and decided that the alpha value 0.01 Gini index and max depth 2 max leaf node is good. And another time it has taken the other sample and it has decided the same exact value for that sample as well. So that means the best sample split, when it does 2 times, it is getting the best result. Even if it does like 3, 4, 5, 6, if it is getting the same results or similar result, then it will ask you to, and then it will show that only 2 sample splits are okay in this case. Sorry, in this case, you don't need to go for further splitting. So what happens here is, if you choose this methodology and suppose you have 2 million rows of data now, and suppose this is one entire data is our sample 2500 rows. Now you've got the best hyperparameters. You don't need to perform a grid search approach. You can simply put these hyperparameters on the entire data, okay, and get the results, get the prediction, accurate predictions. So that's the basic concept regarding the entire grid search approach and what these things mean. Okay.
Okay. And you also did some multiplication in the beginning, like features
Yeah.
and maximum depth. What was that?
So exactly. So that is basically a combination. So you've studied permutation and combination, right? So there are 3 features here. 6 features here. 1, 2, 3, 4, 5, 6. Okay, and each time, in every iteration, there are 2 parameters here. 2, 4, 5. 5 parameters here. So altogether there are 16 parameters. So 16 times 16 values of these parameters multiplied by 18 parameters altogether. 18 values of these parameter multiplied by 6 is the combination for each time an iteration will be performed. So it will check square root with 2, Gini, 2, 1.01. Again, it will check square root with 4, Gini, 4, 2.02. Okay. Similarly, again, each and every combination. So it makes 108 combination for each iteration that it is making. Just simply I'm multiplying it. Okay.
Got it, got it, got it. So basically, in the result set, we will have 1808 value if we leave it to run it as it is. 108
Yeah.
answers.
Processing speed is very fast, although. So that's why even the 108 combination in each and every iteration, it is performing very fast, considering that it is performing for 1750 rows as a training set. Okay. And then finding out the value for you. Now, yeah, so that's the entire concept. Sorry.
Got it, yeah. Thank you.
Anyways. So evaluation metrics, again, 83 is what we are getting. Recall, we're getting the similar numbers. AUC curve is 67.15. Now, if we move on to random forest, similar, apart from the values that we have got here in the
We can
decision.
apply boosting also, no algorithm
Yes, you
for
can
better accuracy.
you can apply XGBoost method here.
Light
Also,
GBM.
yeah, you can apply boosting method as well. So on top of it, okay, and that's something which I wanted to give you as homework. Okay, on top of random forest also you can apply boosting method. On top of decision tree also you can apply boosting method. Try it on your own, see if you can get improved result. Okay.
They
So
are belongs to same family, ensemble family, no? Both the
yes,
random forest and XGBoost.
yes, so what happens here now, what happens in XGBoost is basically any boosting technique. What will happen is when you consider tree, okay, and each leaf as your data point, okay, and consider an entire forest of trees, okay. When the random forest chooses the best parameters in terms of the data, it not always considers the entire data points, okay. Some of the leaves are left behind, okay, and those leaves are basically called stubs, okay. Those stubs are left behind, okay. And what XGBoost does is basically tries to consider those stubs as well, okay. And those stubs are basically taken all together into consideration for better learning, and that's why it gives improved result. Not necessarily, not always it will give you improved result, because sometimes those stubs are not significantly important to be considered. So sometimes that happens, but you can always give it a try. So what I would suggest is try some boosting methods, see if you can improve the results. Okay. Another thing is there are a few other methods. As you can see, this is a grid search approach. There's a randomized search approach as well. What happens in grid search and randomized search? Grid search considers each and every data point. Randomized search randomly takes a sample out of the data and then tries to find out the best uh, features for you, best hyperparameters for you. Okay. And then gives you the final prediction. There is another way. There's a third method, which is called what it's called. Sorry, I forgot. I had to check. It's called binomial something method. So searching yeah, Bayes search. Okay. You can try, you can avoid these things, but the best obviously it's manual search, but yeah, grid search, randomized search are the two most used, but I would suggest you can try Bayes search as well. Okay, Bayes method. And there's something called binomial search as well, but that is only for a binomial classification, but yeah, avoid that as well. Okay. So try randomized search. I would say if you have a large data, okay, and if you have a large sample, basically, because usually we perform grid search on a sample first, okay. So try that. Try randomized search if you have a large sample. Then definitely try Bayes search method as well. Okay. Once just give it a try, see if you can get better results. Okay. See, everything cannot be discussed in 2 hours class, so that's why I have limited these things to certain most important things that I want to discuss, and giving you the option to try. If you are enthusiastic enough, you will try the things that I have said. Okay. If not, then these things are also good enough to crack the interviews. Okay. But if you want to go deep down into the depth of data science, obviously you can try these methods as well. Okay. So most of the values that we have seen are same, only the estimators. It is estimating that how many number of trees that it is going to take in the entire forest, either 10, 100 or 1000. Okay. You can give more values as well if you want, but again, it will eat up the computation power that you have from your system. So right now it is taking the estimators as 10 and giving you the best result. So it has improved the accuracy to 60, almost 67%, 66.9. And when you compare the recall, it is 70, and the classifier, the precision is also 70. So you can see that the precision and recall both are 70, 70. So it has not improved much. But again, if you have better, I would suggest if you have more data, and if you keep it to more number of estimators, this can change. Okay. So in my case also, in the entire data, decision tree with applied along with some boosting techniques gave me better results. Okay. And if an interviewer asks what was the level of accuracy that you achieved, you can confidently say 89. Not the accuracy, you can say that we reached to a level of accuracy with 72%, but the most important KPI for us was recall, which was 89, which we reached. Okay. And it was good enough to say that, yeah, 89 out of 100 times we are predicting the right prediction to say that whether the patient was eligible for operation. But I'm telling you the story about the entire data. Again, when you feed the entire data to the model, it learns a lot rather than feeding 2500 rows. Okay. But again, I had to show few things to you, and that would have taken a lot of time into running the model. So even in this data, with these hyperparameters, this random forest takes 10 minutes, more than 10 minutes, I think around 15 minutes to run for me. And that too, I have an M1 chip with a TensorFlow powered device, so you can understand. So if you see the results here, it is saying that the true positive and true negative cases, it has been able to predict very nicely. So again, the recall is 70%, but these numbers, the false negative and false positives, are very high, significantly high when you compare it with the decision tree. So 67 here, 173, but at least the false negative cases are pretty much minimized. So that is a good indication. And true negative cases are also correctly identified. So that is also good indication that our decision tree is performing better when you compare it with the 275 with the 328 value and 67 with the 120, which we don't want. So and overall value as well. So it's 70 and it is 83. So it is giving us better results. Again, when you see AUC, it is very much in line with the accuracy. So it's 68.33. Now, in terms of the results that we have got as of now, the best model is decision tree. Reason being is when you compare the recall of random forest and decision tree.
Rahul, sorry to interrupt. I missed one point. Like you said, like in interview that KPI is recall, and I missed that point at the time. I have a network glitch. Can you repeat that statement once again?
Yeah, sure. So in interview, when they'll ask that what was the most important KPI for you, you can say that, yeah, obviously we set up some benchmark using accuracy, but recall was the best KPI in medical cases because it was truly identifying the those cases which are basically significantly labeled correctly. Okay. So when you go by the definitions of recall, you will be able to understand that what I'm talking about. Okay. And that's why that was important. So in case, for an example, if we are allowing our patient to go freely if they're eligible for an operation, and they die on the spot or maybe next day, then that becomes a problem. But in those cases where we are not trying to, when even if the patient is eligible for operation and we are denying that operation, then and if the condition deteriorates, or the doctor sees that the level of criticality of that patient is high, then they can check that case manually. But it saves, and if we are giving a recall value of 89%, then that means that 89 out of 100 times we are saving time for the doctors, and at least for the level 1 and level 2 criticality, they can say that they can rely solely on us. And in those cases where the critical patient is the level of criticality of the patient is level 3, okay, and we are denying operation, then they can check those cases manually, which right now for the entire data we can say that 89 out of 100 times we are predicting correctly. So 11% of the data, 11% of the patient can be denied operation in that cases. But when you see that the level of criticality is, when you only check for the level of criticality high, then that number also goes down by 11% to 7 or 8%. So that saves a lot of time for the doctors, and in turn saves a lot of money for the entire hospital as well. Okay. Make sense?
Yeah, Rahul.
Rahul, one question. Like in the random forest, we have the data which is not being picked up by the random sampling, correct? So that data will be terms like that data will be used for testing with the help of OOB score, something like that. Some term is that
Score
OOB,
OOB,
out of
yeah,
out of the
yeah,
box.
auto bonded, yeah.
Actually, that data was not used in the tree formation, and that can be used as a testing set, correct? So XGBoost work on that data.
Uh, See, if I tell you based on the data, it won't be correct, because even though the random sampling that the random forest does, it basically tries to cover as much as data as possible. So when it does the sampling, when you give the number of trees, number of estimators, 10, 100, 1000, okay, it tries to take all the values from the sample altogether. So suppose there's a bag in which you have 1000 data points, and there are small bags from a larger bag. You're transferring data to the smaller bags. Okay, that's what happens in random forest. So it tries to find out, and there's 1000 data points, so 100 data points are taken into one bag, and 10 and there are 10 bags, so 100, 100, 100. Okay, there's a possibility that similar type of data in bag number 1 and bag number 2 are present, but there's a possibility that there are different types of data. Okay,
Correct.
so what happens, it not happens at the level of sampling. Basically, what happens when you go to the next step? Okay, now that sampling is done, okay, each and every data point basically is assigned to each and every node. Okay, and each node contains branches and leaves. Okay, and suppose when you consider the criteria at each and every node of a decision tree, and random forest is a collection of decision tree. At each and every decision tree, suppose it is giving yes or no after a criteria, Gini criteria or entropy criteria. Okay, it gives you yes or no, yes or no. And when the final voting is counted, okay, for yes or no, okay, sometimes just before the final voting, and when you're doing the decision tree sampling, okay, those nodes which are containing all the branches and all the leaves, some of the leaves are left out of that combination, and those leaves are not considered because they are considered less significantly important. So suppose in our case, when you, I mean, I'm going very deep
No, no,
into it.
I'm aware of that point. Like some of the rows are not present in all the leaves
Yeah,
because they are not important.
yeah,
Just
connected with
information.
the,
Yeah.
yeah, when you connected with the coefficient of Pearson coefficient of correlation. Again, urological.
But inbuilt, it is having the features selection so that it will eliminate unnecessary rows or columns, which is not correlating with the target, which won't
Exactly.
affect the target.
Exactly. So in our case, urological could be one variable in which, if it is present as one of the decision maker, it can be avoided by random forest. Okay, but there can be cases, in just few cases, where it can significantly help in making that decision, or like influence the decision making of that particular decision tree, right? So what happens, even though random forest has left that, because it is not considering that as an important feature or important data point, XGBoost will consider that and play a role in that voting method. Okay, again, what XGBoost does is take those data points, take those leaves, and improve the prediction by influencing that it could be an important feature as well, right? On that particular node, on that particular branch, on for that particular leaf. Okay, but again, it can improve that prediction to a level of like 10%, 20% for each node, for each branch. Okay, and then again, if you take the overall voting, okay, so that can improve very significantly low, or can improve very significantly high, if at all random forest has missed a series of data points which are like very important at some data level, but not at an overall level, because again, it is doing random sampling, so it can miss out on those data points which are not significantly important at an overall level, but few data points can or cannot be important. So XGBoost takes into consideration of those stubs, those data points which are left behind, those leaves which are left behind, and gives importance in terms of voting. But suppose there are 10 trees, okay, and even random forest has picked out 6 out of 10 trees as yes, and 4 out of 10 times it has picked from those trees as the final prediction as no. So overall, after the entire ensemble process, after the voting process, it will say that this particular patient, uh, out of all the equations that we have made, 6 out of 10 times it is saying that this patient should be operated. So my final answer would be yes. Again, in case where it goes from 4 to 5, okay, first of all, it will take into consideration that whether how many number of trees are there present. Okay, but in case where like it changes some of the values at a very deep level of the tree from 4 to 5, then obviously it will influence that factor. But it happens significantly in at those small level, but at an overall level it will not change the prediction too much. Okay, most of the cases, but yeah, obviously it will give you some sort of prediction, 1 or 2 or 3%, but you can understand the mathematics of it, like at what depth it goes and tries to improve the prediction. So at an overall level, it can or cannot impact highly. So that's the problem.
So basically, XGBoost will go to each decision tree and go for that part.
It
The
will go
random
to
forest.
each of the decision tree. Yes. Yeah.
Each of the okay. And what is OOB then?
So OOB is another method to minimize the error. So it calculates the number of error, which the value of error. Okay, and then it becomes a deciding factor whether at particular branch, at particular node, whether the level of error is high or low, and based on the lowest error method, it tries to find out the best prediction for you.
Okay. Okay. No.
You're talking about the OOB out of bound error, or within the trees, or you're talking about evaluation that
Evaluation. I think OOB can be used in the training part and can be used to calculate the accuracy.
I was talking about the error method. The evaluation is OOB evaluation is basically to evaluate the quality of the model, basically.
Okay.
And yeah, it happens in the training set, but it's very much related to cross validation concept. So Basically, what happens is like when some data points fail to be a part of a particular sample, then that out of bag evaluation method is applied, and then that also is considered. But again, it's when you compare the methodology, it is similar to XGBoost, but again, boosting techniques do not interfere with the sampling. OOB interferes with the sampling. That's the difference.
Okay.
Yeah, final bit, whether what we are doing here makes sense or not. Okay, statistically, so you would have done t-test on like before deciding the sample, before deciding whether this particular data makes sense or not, whether the hypothesis that you have that you're thinking should be true, before applying the machine learning algorithms. Okay, these things you must have done. What we are trying to do here is, and this is basically, even I didn't know, I came to know about it after completing my master's degree, that we can use t-test on what OB, what is abbreviation? It's not OB, it's OOB. Yes, so it's out of bag evaluation method.
Out of
Yeah. Yeah, so best model, we will say that it is decision tree, because when you compare the decision tree with the recall value of decision tree, and now that we have a similar recall value with logistic regression. Okay, and when you compare the results, obviously, and when you compare all the results like AUC curve and accuracy, everything, since we are getting similar recall and precision, you can see that it's slightly edging towards the
Rahul, we can go through this blog related to out of bag.
let me check. Bag score looks okay to me. I'll have to look at it at depth and check if it makes sense. Okay, but yeah, I mean, the algorithm, you can look at it yourself. Yeah, obviously, if it is, I mean, everything that is mentioned in analytics vidya can or cannot be true. Even on Medium, I have found mistakes. So I'm not sure. I prefer going to a very traditional method of like going through research papers rather than following these. And I really appreciate the use of books and research papers rather than these. So yeah, and I'm not saying that these are wrong. I'm saying that it's taken because of a result of one sample or one data. Okay, they check it and then publish it. But yeah, when you read a research paper, it is usually performed on multiple data sets, and it is tested significantly. That's why it's published. So I would prefer that method over this. But yeah, I mean, by all means, if you want to go through it.
Research paper we can see in Sci-Fi Hub, or what are the website we can get?
IEEE, you can go to IEEE, just simply go to Google Scholar and check for IEEE papers on OOB, and you can get them. Okay.
Rahul, one thing, can we also use bagging in case here?
Bagging, yes, you can use. Yeah, obviously you can use.
Bagging by combining multiple different algorithms and then try it.
Yes, you can try. But again, when I'm saying that you can try these things, okay, you have to consider one factor importantly, and that factor is time. Okay, computation power of your system, and your obviously the cost of it. So you have to take a decision very carefully. You can just not go ahead and simply choose all the algorithms that you want. Okay, best way to do is like find out the do a proper data analysis and find out whether it is following any pattern, any linearity, non-linearity, and based on that take a decision. Okay. Simply right now for practicing, obviously you can try 10 different methods and that should be fine. But again, when you uh, go for an interview, you have to be very selective, and when you go into job, you have to be very, very selective. Okay. An extra level of selectiveness should come, because it will eat up your time. You'll have to explain that what you are doing to your chief data scientist, because every time you'll have at least one person who will be monitoring your work. Okay. And if you're doing anything out of blue, then they will understand that what you're doing is not correct. Okay. So you have
Okay.
to take decision based on your data, first of all. Okay. So
And
do
and
proper
one
data
one
analysis.
one thing more, like as per the correlation coefficient, if our that basically tell us the linear relationship between our variables, correct?
Yeah, yeah.
Our independent variables. So if that value is high, in that case our model is basically having linear probability, correct?
Uh, when you're saying that when you're comparing two independent variables, then it is basically a case of multicollinearity. When you're comparing an dependent and independent variable, then it says that, yeah, the relationship is linear.
Okay,
Okay.
okay. Yeah, on the basis of that we can basically select our algorithm, like which
Exactly.
algorithm will be good, correct?
Yeah, exactly.
So if multiple independent variables are basically having the linear relationship with our target, so in that case we can say that is the linear behavior in our data.
No, no, no. If multiple variables are having high correlation coefficient, so suppose 70, 80%, that is fine. That means that your data is linear, that is fine. But if multiple independent variables are having high correlation coefficient within themselves, okay, so there are two ways to check correlation. Yeah. So if this bit is high, okay, very good. If criticality and say suppose where is it? Suppose blood and urological. Okay. So blood and urological. Yeah, blood and urological. So this, if you consider this value, it's minus 0.16. Okay. If it is like 0.80, 0.90, and if you consider heart and blood, okay, it's 0.24. If it is like 7.70, 0.80, okay, and that means whatever indication my blood is giving, same indication my heart is giving, same indication that my urological column is also giving. Okay. So that basically means that we are feeding the same pattern to the pattern of data to the model. Okay. And which can result into repeated
Multicollinearity.
learning. Basically that means which can result into if it is repeated learning, that means it can result into uh,
Rupesh, it can't be a multicollinearity. See, multicollinearity is basically like if a feature is highly correlated with another feature which is a part of independent variables.
That's exactly. So that's what I'm explaining. Blood and urological, heart, they are all independent variables here, right? And if they are like highly correlated to each other, that means they are feeding the same type of information to the model. Okay, which means that it will help into either over prediction or under prediction. Okay, so that means like it can overfit the model or underfit the model. If it is like negative coefficient correlation, then underfit the model, or like if it is contribute to underfit. I'm not saying that it will definitely do that, but it can contribute. And one of the so logistic regression is designed on the concept of linear regression, basically, if you know that.
Yes,
And
yes.
the one of the things that you have to avoid in the equation based models in terms of in any model basically is to avoid the multicollinearity. You cannot have multicollinearity in the data. So, yeah.
So basically, how can we decide that our data is linear?
So yeah, I mean, you can decide by looking at the dependent and independent values. So if my operation column here, okay, is saying that 0.38 and 0.28 instead of 0.38 and 0.28, it is saying that not only 30 and 40%, it is 70 and 80%. Then that means that it is following a linear relation between two columns. So suppose there is x-axis, which is operation, and y-axis, which is criticality, and if the data points are like this in the line, okay, that means it is having a linear relationship, but it is like 0.38. So maybe in some points it is linear, but in some cases it is not. So it is only 40%, around 40% linear, but 60% of the time it's not linear. Okay.
Okay, okay,
So
got
that's why. So that's why when we check the results, when we saw without the use of hyperparameters, where is it? Yep. Without the hyperparameters, the recall value was 68. Okay. But when we introduced some of the solvers, okay, it checked the non-linearity of the in the data as well. Okay. And it improved the prediction significantly by checking the non-linear methods as well, and it improved it by to 83, I think, right? 83. Yeah.
Yeah, got it.
Okay, so last bit, very quickly, we are already above and beyond the time. So yeah, so t-test is used to compare the samples. Okay,
Like t-test is used less if sample is less than 30, then only we can take the t-test on our.
yes, you can take.
So like if toxicology, for example, if the level of the toxic data is we can check according to the statistical way, no?
Yes, you can check. Yeah, of course, you can.
Yeah.
You can do that. Yeah, you have to.
So yeah, alternate way of multicollinearity, we can try to use the chi-square test, no?
You can, but only if you're not able to perform a Pearson coefficient. So chi-square is a bit complicated, and it is used to compare the data if you have a categorical variable and if you have a continuous variable, and if you want to compare those. Two categorical variable. If you want to compare those two, then you can use chi-square. And yeah, there's another method. I always forget the name of that method. When you come, just check it on internet. There is another method when you have to compare a categorical variable with continuous variable. Then also you have to compare it with that particular correlation or coefficient. That method. Sorry, I forgot the name. I'll have to double check. But yeah, chi-square, when you have two variables which are categorical, then you can use chi-square to answer your question. These statistical tests are performed on top of the sample values from the prediction. Okay, and what it says, this indicator means that whether the entire work that we have done, it does not prove anything for sure, but gives you a strong indication.
That
Okay,
is ANOVA you're talking
which,
about, like
not on
categorical and ANOVA.
not on a hold on. Yeah, point based result test. It is more, I mean, it's better than ANOVA in some cases. The data should be obviously normally distributed. We can use something known as point based correlation. Yeah, forget the name of it always. It's a weird name it has, but yeah, you can use point based method. Obviously, you can use ANOVA, but I was not emphasizing on ANOVA. Point based method gives you better. I mean, in my experience, it has given me better results in comparison. But yeah, by all means, you can go to ANOVA as well. But I would want to suggest try point based test as well. Okay. Yeah. Finally, yeah, t-test that we are doing here is not on the sample of the data. We are doing the test on sample of the values that we are getting in terms of the results that we are getting, logistic regression and logistic regression with hyperparameter tuning, logistic regression with decision tree and random forest, and obviously logistic regression with random forest. What it says is if it is greater than 0.05, then it is statistically significant. If it is less than 0.05, the p-value, it is not statistically significant. That means if it is greater than 0.05, okay, that means the work that we have done is null and void. Okay. Basically, even if we don't do it, it's fine. Okay. And if at all, what we have done in terms of prediction, when you compare the results of one model with the other, then it gives you statistical significance, whether it was worth checking the results or not. But again, it's a strong indication. It does not tell you whole story. Okay, but you can perform these tests to prove a point if somebody asks that whether it was important to perform the decision tree, random forest, logistic regression, or you're getting the same result. So again, when you test logistic regression with hyperparameter tuning, it says that yeah, it is very less than 0.05. As you can see, e raised to -11. Okay, so logistic regression with hyperparameter tuning was worth checking. Okay, this statistic value is basically a t-test statistic value. Anything which is above +2 and which is below -2 gives an indication, strong indication that whatever we have tested is fine. Okay, above +2 and -2. When you compare the result of logistic regression decision tree, it says p-value is equal to 1 and statistic is equal to 0. That means that whatever result we were getting from logistic regression, we're getting the similar result from decision tree. So unless you're getting something which is like evident enough to prove something which is like evident, like a jump in accuracy, a jump in one key performance indicator, you can or cannot choose to use a decision tree or logistic regression model. When you compare decision tree and random forest, you can see that there is a significant value which is less than 0.05. Again, it is more than +2, so both are strong indicators that you did a good job spending time to design the decision tree and random forest. Again, when you compare logistic regression with random forest, it says that a p-value is greater than 0.35. So the results of logistic regression and random forest are also very similar to it. Okay, so in tree-based models, you can see logistic regression and random forest. When you tried, it was fine. In equation-based model, when you tried logistic regression simply and logistic regression with hyperparameter tuning, it says that it is fine that you spend time on it. Okay, but since these two methods are, and especially when you talk about hyperparameter tuned method, okay, with the decision tree. So when I'm now comparing log reg, which is like tuning which is tuned hyperparameter results, okay, with the decision tree. Now, if I change it to normal logistic regression without hyperparameter tuning and run it, you can see that it has increased, it has changed. Now it makes sense to spend time without doing hyperparameter tuning. If you do jump onto decision tree, now it says that it makes sense that you did that. If you do the same with the decision tree, it will tell you the same story. Okay. No, sorry, it is decision tree with random forest. Sorry, did it wrong.
So difference can be positive or negative. That is not explained, correct?
Difference can be positive or negative. That's not the point. So this statistic value, that is t-test statistic value, the range of it is like, if it is like above 2, then also it's a strong indicator that the prediction that you have made is basically correct. And if it is less than 2, then also it says that the prediction that you have made are statistically significant. They are different from each other. They're not telling you the same story. They're not identifying the same pattern. So you can spend some time finding out the best model for you when you compare logistic regression and decision tree, rather than simply following the traditional method. So t-test indicates that the results are statistically significant when you compare logistic regression with the logistic regression with hyperparameter tuning and the decision tree in random forest as well. But when you compare logistic regression with random forest results, then it is not. So it is increasing by 0.05. So that means that it is not worth spending. So that's the indication when you compare the results. Again, the application of it is very simple. Okay. Right now, what we are seeing here is number of patients, okay, with different patient ID, okay, and they're all medical condition, and based on that, we are getting a prediction whether the patient should be operated or not. Okay. Now, this particular test becomes very, very important. Okay, when you do a time series, when you do an analysis on a time series data. When I'm saying time series data, it not necessarily means that I am performing time series algorithms on top of it. Time series data means for each patient ID, okay, if you have a historic data in 2011, the right now it's an average of blood, urological, blah, blah, blah. Okay. When you have a data, suppose in Excel sheet, I want to show. Suppose this is a patient ID. What is it? Okay. And I have this urological, sorry, blood condition in 2017. And until 2021, we have data, suppose. And this is 1, 2, 3, 4, whatever. Okay. So this sort of data, right? It can be whatever. Okay. So suppose this is kind of data for each patient ID, your model is getting this data for just one parameter blood, okay, for each year. Okay. And same goes for urological, same goes for lung, blood, bone, etc. Right? It has data of past 4 years, how it has changed over the years, right? And then if you make prediction, okay, then what happens is for each patient ID, your model basically learns these things, okay, each time. So each time your model runs, for each time all the iterations are performed, all of these iterations, all of these hyperparameters run for each row of your data. Okay, you understand that? And each time it tries to learn from your data and then gives predictions. Suppose instead of this particular yes or no, you want to get an average value from, right now what we have got here is an average value altogether from the main data, but you want to get a prediction of that and narrow down your number of variables. Okay, so each time if you perform it, then each time when you get the prediction out of this out for this patient, so your model runs with all the hyperparameters each and every for each and every row, each and every time, and it gives you prediction at each and every level of so suppose prediction is this much. Okay, each and every time it gives you a prediction by learning from this data. Okay, suppose it is learning from this and these two data points are getting for tested, and based on that it is giving you the final prediction. Okay, now suppose this prediction has come from logistic regression. Okay, and there are other models, decision tree and forest. Okay, and you have the same sort of data over here, but maybe different prediction. Okay, yeah. Okay, now when you compare these prediction based on that, then it becomes a statistically significant value. Okay, much more statistically significant value, because now it is comparing for each and every patient's exact value. Okay, and based on that it is calculating the p-value and giving you the result. Okay, ultimately how it helps is when you see the error value, when you calculate the error value, okay, by actuals minus prediction from your test data, from your trained data and test data, then the least error method, okay, based on either mean square error method or whatever. So suppose there is 75, whatever, okay, something it is coming. So you can design a model based on the error of these three values and choose the best one. Okay, so that will give you the most accurate result. So suppose in this case, the least error is logistic regression. So there will be a best model column, which will give you log rank for each case. So it will turn out to log rank. So for patient ID 567587, the best model has come out to be log reg. So whatever hyperparameters that you have set for log reg, that will only be counted. So these hyperparameters will be counted for your final prediction. So in that case, it helps. But now where we have this sort of data, which is not time series data, in which we have like taken into account of all the data all together, okay, this is good enough. Okay, but this is just to give you a feel that you might or might not get a data which is very specific to a particular patient or a particular client or a particular company. You will have historic data and then you'll have to make prediction. You'll have to take the average value and then do it, make it as a final prediction, or make use of it as your this predictor value can be a final or can be used as an average value to another outcome that you want to calculate and can be used as one of the features. So this is one of the method that you can apply. Okay. The methods that we are using is pretty straightforward. We are using just mean squared error method and taking the best model based on the least mean square error method, right? But we are comparing the results of these models and choosing the best model for us. Okay. And whether these results, these predictions are significantly significant or not, basically, we can test these results by using t-test. And then if that t-test says that no, whatever prediction that you're getting, suppose in this case, where we are getting 0.35 for decision tree and random forest. Okay. No, sorry, no, this is not the case. Yeah, I mean, in this case, decision tree and random forest, it is saying that it is less than 0.05, which means that it is identifying that this value 86968 and 87,687 are statistically different. And that's why it says that go to the next step and go and see what is the mean square error. Okay. And then find the best method out of decision tree and random forest. If at that point your statistically significant result does not come to be true, whether when the t-test says that your random forest and decision tree are exactly the same, if it is throwing you a value of greater than 0.05, which means that you don't need to go to mean square error and perform the best model and then do the feature selection out of the results of decision tree and random forest. Okay. So this is the level, this is a depth of statistics which is involved in your machine learning concept when you design an entire model. Okay. But depends on case to case. There could be simple cases which can end here, which was the case for me. But this is just an extension which I probably shouldn't have told. But yeah, it is just for your knowledge sake that you can use these methodologies to find the best models.